In this session, I am going to discuss about numerical integration, which is a subtopic from Unit 5, Numerical Methods 2. Let me begin this session by recalling what we have studied about integration. Integration is a way of adding slices to find the whole. We have come across with problems such as finding area under the curve, finding velocity of a body from an acceleration function, displacement of a body from a velocity function, center of mass, center of gravity, mass momentum of inertia of a sports utility vehicle, predict the position of planets, and even in electromagnetism, in which we use the concepts of integration to solve them. Integration of functions like sin x square by x, e power by x analytically is impossible. We also come across with integrals whose evaluation is complicated and time consuming. In many cases, analytical methods fail. So in such cases, we think about an alternate way of solving, which is nothing but the numerical methods. Look at the table carefully. The values are tabulated from the observations of an experiment. X is varied from x0, x1, x2 to xn, and the corresponding y values y0, y1 to yn are tabulated. The process of evaluating the definite integral x0 to xn f of x dx from the set of tabulated values of f of x is called numerical integration. Numerical integration is basically finding the area below the curve, which is shown in the first figure. The basic idea of numerical integration is to approximate continuous function with discrete points to approximate integral, which is shown in the second figure. Now let us discuss the various methods to solve numerically. The first method is curve fitting. In curve fitting, we fit a curve to the observed values and analytically integrate curve and hence find the solution. The second method is Newton-Cotes integration. In Newton-Cotes integration, complicated functions are tabulated and they are evaluated. Here what we do is we replace with approximate functions, which may be easy for us to integrate. When we try to replace with approximate function, that function can be a single function or piecewise polynomials. The rules used here are the trapezoidal and the Simpson's rules. The third method is Gauss quadrature integration, and this method is applicable when the function is known to us. This figure is an example for Newton-Cotes integration. The curve y equal to f of x is approximated by a single straight line in the first one and by a parabola in the second one. One of the Newton-Cotes integration formula is trapezoidal rule, which is the simplest one. Here in the figure, the curve y equal to f of x is approximated by a straight line and the area below is nothing but a trapezoid. The second Newton-Cotes integration formula is the Simpson rule. Here the curve y equal to f of x is replaced by higher order polynomials. 3 points make up a parabola and 4 points make up a cube. The two types of Simpson rule are, the first one is Simpson's 1/3 rule. Graphically, it consists of taking the area under a parabola connecting 3 points, and that is shown in the first figure. The second one is the Simpson's 3/8 rule. Graphically, it consists of taking the area under a cubic equation connecting 4 points, and that has been represented in the second figure. Simpson's 1/3 rule is demonstrated here. Figure represents the graph of the function y equal to f of x. A parabola is fitted through 3 points, which is a second order polynomial. Let us now discuss about Simpson's 1/3 rule. Given I is equal to integral x0 to x0 plus nh, f of x dx. Here f of x takes the values y0, y1, y2 to yn for the corresponding values of x, which is x0, x1, x2 to xn. Let us divide the interval x0, comma x0 plus nh into n sub-intervals of width h. So x0 would be equal to a, x1 is x0 plus h, x2 would be x0 plus 2h, x3 would be x0 plus 3h, so on to xn is equal to x0 plus nh. I call that is equal to b. So the Simpson's 1/3 root formula would be integral I, which is x0 to x0 plus nh f of x dx, and that is equal to h divided by 3 times of y0 plus yn plus 4 times of y1 plus y3 plus so on to yn minus 1 plus 2 into y2 plus y4 plus so on to yn minus 2. Here h is b minus a by n. Please note that this formula we can only apply when the number of sub-intervals is a multiple of 2. Let us now discuss about Simpson's 3/8 rule. Given I is equal to integral x0 to x0 plus nh f of x dx, where this f of x takes the values y0, y1, y2 to yn for the corresponding values of x, which is x0, x1 to xn. Let us divide the interval x0, comma x0 plus nh into n sub-intervals of width h, such that x0 would be equal to a, x1 is x0 plus h, x2 is x0 plus 2h, so on to xn is x0 plus nh, and that is equal to b. So Simpson's 3/8 rule formula will be I is equal to 3h by 8 times of y0 plus yn plus 3 times of y1 plus y2 to plus y4 plus y5 plus so on to yn minus 1 plus 2 times of y3 plus y6 plus so on to plus yn minus 3, where h is b minus a by n. When we observe this formula, how easily you can remember is that when you write down the formula, I would be equal to 3, h is the width, which is the step size, divided by 8 times of y0 as the first value in the tabulated values and yn would be the last value. So y0 plus yn, the first value plus the last value, plus you can see there 2 times of, when you look at the ordinates there, it is y3, y6, y9, y12 and so on. So we can remember that as 2 times of the multiples of 3, and the remaining terms what all is left out, which is 3 times of y1 plus y2 to plus y4 plus y5 and so on to yn minus 1. This is how easily you can remember this formula. Let us also note that this formula we can only apply when we divide the sub-intervals, which is be a multiple of 3. Let us now discuss about Weddle's rule. So again, let us consider the integral I is equal to integral x0 to x0 plus nh f of x dx, where f of x takes the values y0, y1, y2 to yn for the corresponding values of x, which is x0, x1 to xn. Let us divide the same interval into n sub-intervals of width h, such that x0 is equal to a, x1 is equal to x0 plus h, x2 is x0 plus 2h, so on to xn is x0 plus nh, and that is equal to b. Weddle's rule is equal to, which is nothing but I is equal to 3h by 10 times of y0 plus yn plus 5 times of y1 plus y5 plus so on to yn minus 5 plus so on, plus y2 plus y4 plus so on to yn minus 2 plus 2 times of y6 plus y12 plus so on to yn minus 6 plus 6 times of y3 plus y9 plus so on to yn minus 3. So when we look at this formula, it seems to be very complicated, and how easily you can remember this. So what we do here is, let me say that you have n to be equal to 6. That is, you have only 7 values. You have subdivided the interval into 6 equal parts. In that case, the formula would be I is equal to 3h divided by 10 times of y0 plus 5y1 plus y2 plus 6y3 plus y4 plus 5y5 plus y6. So look at the pattern. You see the coefficients of each term there. The first coefficient is 1, the second coefficient is 5, again the third coefficient is 1, the fourth coefficient is 6, then again the next coefficient is 1, the fifth coefficient is 5, the last coefficient is 1. It is following one single pattern there, that is 1, 5, 1, 6, 1, 5, 1. So when the number of subintervals is equal to 6, the formula is, which is listed here. Same way, when the number of subintervals is equal to 12, the formula would be 3h divided by 10 times of y0 plus 5y1 plus y2 plus 6y3 plus y4 plus 5y6 plus y6 plus you start again with y6 and end with y12. So you get plus y6 plus 5 times of y7 plus y8 plus 6 times of y9 plus y10 plus 5 times of y11 plus y12. So we can only divide the subintervals which would be the multiple of 6. So you can have n to be equal to 6, 12, 18 and so on. This is how easily you can remember this formula. Please remember the pattern. It is like 1, 5, 1, 6, 1, 5, 1. Again you start with 1 and you end with 1. So 1, 5, 1, 6, 1, 5, 1. Now let me consider an example. Evaluate integral 0 to 6 dx divided by 1 plus x square. I need to evaluate this integral using Simpson's 1/3 rule, then Simpson's 3 by 8 rule and Weddle's rule. So now what we do is, let us divide this interval into 6 equal parts. See, we know that Simpson's 1/3 rule can be applied when n is a multiple of 2. Similarly, 3 by 8 rule can be applied when n is a multiple of 3. And similarly, Weddle's rule can be applied when n is a multiple of 6. So since it is multiple of 2, 3 and 6, we will subdivide the interval into 6 equal parts. See, h is given by b minus a divided by n. So b is nothing but the upper integral, which is 6 minus 0 divided by 6, and that is equal to 1. So which size is h is equal to 1. So you start with x is equal to 0 and increase by 1 so that you end with 6. So x takes the values 0, 1, 2, 3, 4, 5, 6. The corresponding y values, which is equal to 1 divided by 1 plus x square. You substitute the values of x there and calculate the corresponding values of y, which is tabulated in the table shown here. And y takes the value 1, 0 0.5, 0 0.2, 0 0.1, 0 0.0588, 0 0.0385, 0 0.027. We need to evaluate the given integral using Simpson's 1/3 rule. So let us do that first. The formula is h divided by 3 times of, see, first value plus the last value. You can look at the table given. The table has 7 values starting with x0, x1, x2, x3, x4, x5, x6. Corresponding y values are y0, y1, y2, y3, y4, y5, y6. The first value is y0, the last value is y6. So that is why in the formula we have written it as y0 plus y6 plus 4 times of, you look at the suffixes there, it is 1, 3, 5. So y1 plus y3 plus y5, they are all odd suffixes there. So y1 plus y3 plus y5 plus 2 times of y2 plus y4, they are all even suffixes, even ordinates. So when you look at the tabulated values there, y0, the first value is 1, the last value is 0 0.02327. So 1 by 3 times of 1 plus 0 0.027 plus 4 times of y1 is 0.5, y3 is 0.1 and y5 is 0 0.0385. Those are sum them. We have added them together plus 2 times of 0.2 plus 0.0588. So when you calculate this value, the value we get is 1.3662. So this is what we obtain by Simpson's 1/3 rule. Now let us solve the same problem by Simpson's 3/8 rule. The formula is 3h divided by 8 times of y0 plus y6 plus 3 times of y1 plus y2 plus y4 plus y5 plus 2 times of y3. I think all of you remember I had mentioned telling that y0 plus y6, that is the first and the last value, plus 2 times of the multiples of 3, which would be y3. We will not write down y6 again there because the last value is y6, which is already written down, plus 3 times of the remaining terms, which would be y1 plus y2 plus y4 plus y5. So the values from the table are being substituted here in the formula, and it has been calculated, and finally we arrive at the result 1.3571. Again, we should solve the same problem by Weddle's rule. So the Weddle's rule, we follow one pattern, which is 151, 6, 151. And I think you remember here n is equal to 6. We have subdivided the intervals into 6 equal parts. So the formula is 3h divided by 10 times of y0 plus 5y1 plus y2 plus 6y3 plus y4 plus y5 y5 plus y6. So substituting all the values here and calculating, we get 1.3735. So in this example, we have demonstrated all the three rules: Simpson's 1/3, 3/8 and Weddle's rule. Let me take an example again, the second example now. As the problem is, a solid of revolution is formed by rotating about the x-axis. The area between the x-axis, the line x is equal to 0 and x is equal to 1, and a curve through the points with the following coordinates. So here the values are being tabulated. The tabulated values are given to us. You can see there x is having value 0, 0.25, 0.5, 0.75, 1. The corresponding y values are given 1, 0.9896, 0.9589, 0.9089, 0.8415. So my problem is I need to find the volume of the solid generated here. So the volume of the solid generated is given by integral 0 to 1 pi y square dx. So now let me apply Simpson's 1/3 rule here, because h is equal to 0.25 and you can see the number of subintervals here. It is divided into 4 equal parts and we have 5 values. So the formula is pi h divided by 3 y0 square, because see, you can see in the formula there, it is integral 0 to 1 pi y square. So all y values are squared. That is why y0 square plus y4 square. y4 is the last value in the table there. So y4 square plus 4 times of y1 plus y3 square plus 2 times of y2 square. So those values are substituted in the formula here, and the answer we obtain is 2.8192. Let us take out another example. The problem tells like this: the speed v meter per second of a car at t seconds after it starts is shown in the following table. Find the distance traveled by the car in 2 minutes using Simpson's 1/3 rule. So here we apply Simpson's 1/3 rule. Let us see the tabulated values. You can see here the time t is 0, 12, 24, 36, 48, 60, 72, 84, 96, 108 and 120. So totally we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 values are there. So it has been subdivided into 10 equal parts. And the corresponding speed has been tabulated in the table given to us. So the corresponding values would be y0, y1, y2, y3, y4, y5, y6, y7, y8, y9, y10, y11. And your step size h is equal to 120 minus 0 divided by 10, and that is nothing but 12. See, the problem was to find the distance traveled. So we know that s the distance traveled in time t is given by ds by dt, and that is equal to velocity. So ds would be equal to v dt. So integral ds would be equal to integral of v dt. Therefore, s is equal to integral v dt. So distance traveled in 2 minutes, and that is 120 seconds, is s is equal to integral 0 to 120 v dt. So this is what we need to evaluate. We need to evaluate this integral. So now, solving the above problem, our basic problem was to find the speed, which is integral 0 to 120 v dt, and we were supposed to solve this by Simpson's 1/3 rule. The formula is h divided by 3, first value plus the last value. First value is y0, the last value is y10, plus 2 times of the even ordinates, that is y2 plus y4 plus y6 plus y8, and plus 4 times of the odd y1 plus y3 plus y5 plus y7 plus y9. So all these values are substituted in the formula, and it has been calculated, and the answer we get is 1,222.56 meters. Now the next method of numerical integration is Gaussian quadrature formula. See, this Gaussian quadrature formula is applicable when the function is known to us. Gaussian quadrature formula is of two types. One is 2-point formula, the other one is 3-point formula. First, let us discuss what is Gaussian quadrature 2-point formula. So 2 points, will approximate it into two functions there. So the integral is from -1 to 1 f of x dx, and that is equal to c0 f of x0 plus c1 f of x1, where x0, x1, c0, c1, these are the 4 unknowns which we have approximated the function. I need to calculate them, and here c0 and c1 are called the weights, x0, x1 are called the abscisses. So when we try to approximate it, we get the values of c0 and c1 to be equal to 1. x0 is -1 by root 3 and x1 is 1 by root 3. So thus our Gaussian 2-point Gauss-Legendre formula is given by integral from -1 to 1 f of x dx is equal to c0 is 1, c1 is 1. Therefore, f of x0 is -1 divided by root 3, and x1 is 1 by root 3. f of -1 by root 3 plus f of 1 by root 3. So this is the Gauss-Legendre 2-point formula. This formula is applicable only when the integral is from -1 to 1. But generally you come across with integrals where it is not from -1 to 1. In general, it would be from a to b. So in that case, we need to transform the integration, the interval of integration a comma b to -1 to 1 by using the transformation x is equal to b minus a divided by 2 into t plus b plus a divided by 2. The second one is Gaussian quadrature 3-point formulae. So the integral from -1 to 1 f of x dx is approximated as c0 f of x0 plus c1 f of x1 plus c2 f of x2, where c0, c1, c2, x0, x1, x2 are unknowns and we need to calculate, and c0, c1, c2 are called the weights. And once we calculate them, we get the formulas integral from -1 to 1 f of x dx is equal to 1 by 9 times of 5 times of f of minus square root of 3 by 5 plus 8 times of f of 0 plus 5 times of f of root 3 by 5. So you can see there c0 is 5 by 9, c1 is 8 by 9 and c2 is 5 by 9. And x0 is minus square root of 3 by 5, x1 is 0 and x2 is square root of 3 by 5. So using this formula, we can find the value of the integral. Again, if the integral is from any other interval a comma b, we need to transform it to the interval -1 to 1. Now let me consider an example to demonstrate Gaussian quadrature 2-point and 3-point formula. So the problem is evaluate integral from 0 to 1 dx divided by 1 plus x. So when you look at the integral, the limits are from 0 to 1. So I need to transform this to minus 1 to 1. So to transform x is equal to b minus a, that is 1 minus 0 divided by 2 into t plus b plus a by 2, that is 1 plus 0 divided by 2. So x is equal to t divided by 2 plus 1 by 2. So this is a transformation. So in place of x, we need to substitute t by 2 plus half. So when we go back and substitute in the given integral, the integral gets transformed to minus 1 to 1. Dx is half dt. So divided by 1 plus x is 1 by 2t plus half. So that is equal to integral from minus 1 to 1 dt divided by 3 plus t. And here we are using 2-point formula, and that is equal to f of minus 1 by root 3 plus f of 1 by root 3. So f of x or f of t is 1 divided by 3 plus t. We just have to replace t by minus 1 by root 3 and calculate the functional value, and similarly replacing t by 1 by root 3 and calculate the functional value. And once you substitute that, the answer results out to be equal to 0.6923. Now by using 3-point formula, integral from minus 1 to 1 dt divided by 3 plus t. The 1 divided by 3 plus t is the function which we had transformed the integral there to minus 1 to 1, and that is equal to 1 by 9 times of 5 times of f of minus root of 3 by 5 plus 8 f of 0 plus 5 times of f of root 3 by 5. F of minus root 3 by 5 and f of root 3 by 5 and f of 0 values are calculated, and those values are substituted in the formula, and finally we obtain the value as 0.6926. Summarizing with all the concepts what we have learned, we understand that numerical integration is necessary for discrete data, complicated functions where integral cannot be evaluated. So we have learnt what is called Newton-Cotes formula. In that we have learnt Simpson's 1/3, 3 by 8 and Weddle's rule. They are very good for predetermined or equally spaced data. Similarly, we have learnt Gaussian quadrature or Gauss-Legendre formulas here, which is more accurate, but what is the limitation here is that we need to evaluate the function at some specific points. So the 2-point Legendre is the third order accuracy. Similarly, we have other methods which can also be evaluated, but that is our limitation, we don't have in our syllabus. Thank you students for your patience for learning and listening. For further details and problems, refer the quick learn notes which has been uploaded, and also refer the reference books in the syllabus.